Ever get that feeling, staring up at the night sky and you're just wondering, how did it all kick off? I mean, the really big stuff, right? Where did this whole cosmic roller coaster even begin? Today, we're taking a deep dive into exactly that mystery. We're using Will Kinney's book, An Infinity of Worlds, Cosmic Inflation and the Beginning, as our guide. Now, if you're like me, you love getting into this stuff, but maybe your brain feels like it has too many tabs open sometimes. Think of this as your shortcut, your efficient way into some seriously mind-bending cosmology without needing that PhD first. Kinney's book is quite ambitious. It tries to connect the cosmos with the tiny elementary particles, all to understand the origin. And he brings in quantum uncertainty right at the start, like the universe began with a wobble. And here's something interesting. Kinney's really upfront. He says he's going for clarity, maybe glossing over some finer points, gives some ideas short shrift, as he puts it. He even has this pretty direct take on philosophy of science. Says it's about as useful to scientists as ornithology is to birds.
Though he admits, when you talk about the beginning, philosophy kind of creeps in anyway. Okay, let's dig in.
Yeah, it's helpful to, look back first to really get where we are now. Think about the old picture. For centuries, the view was totally Earth-centered. Ptolemy, Aristotle, they shaped this idea. Imagine Earth, fixed, and then these perfect crystal spheres rotating around us. Moon, planets, stars, all nested. It wasn't just placement, though. It was about fundamentally different realms. Earthly stuff was heavy, needed pushing. Heavenly stuff was different, ethereal, always moving.
Right, two sets of rules.
Exactly. Aristotle's physics laid that out. Everything needs a mover, which, led to questions about the first mover, but it set the framework. Anatole France described it beautifully, those layered spheres, the fixed stars, the primordial. Even in Ninth Heaven, it seemed simpler then. The biggest shift is realizing the same laws apply everywhere now. No special address for Earth.
That's a massive shift from Earth being center of everything to, this much more dynamic, almost chaotic seeming universe. What really started to change that old view?
The big game changer is the standard Big Bang model. It says the universe started incredibly hot and dense, what we often call a singularity. And this isn't just a weird theoretical quirk. Hawking and Penrose showed it's kind of generic. If space-time expands and has stuff in it, you tend to get this singularity in Einstein's theory. So infinite density, infinite temperature. It seems baked into the model. But it's also where most physicists suspect Einstein's theory breaks down. We probably need something more fundamental there, like quantum gravity.
Ah, okay. So the singularity is predicted, but also maybe a sign the theory is incomplete right at the start.
Precisely. And while the standard model explains a lot like the expansion, the light elements, it leaves huge questions open. Why is the universe so big, so old? Where did all the galaxies come from? And crucially, why was the early universe so incredibly smooth, uniform? Kinney really stresses this. Standard cosmology doesn't just fail to answer these, it can't answer them within its own rules because of how general relativity works. It's like a map that just stops right when you need it most.
Okay, so the standard model gets us started, but it has these built-in, areas about the initial conditions. What are the absolute biggest puzzles it leaves hanging?
Well, two stand out: homogeneity and flatness. When we look at the cosmic microwave background, the CMB, the Big Bang's afterglow, it's incredibly uniform. The temperature is almost exactly the same everywhere we look, like unbelievably smooth.
Like a perfectly mixed soup across the whole sky.
Exactly. And then there's the flatness, the geometry of space itself. Our measurements show it's extremely close to being geometrically flat, like a vast, perfectly flat sheet of paper. Kinney points out when the universe was just minutes old, it was flat to 1 part in a trillion. That's astonishingly flat.
Whoa.
And in the standard model, these are just initial conditions. You just have to assume the universe started that way. Perfectly smooth, perfectly flat. It feels unsatisfying, right? Like starting a race with a perfectly tuned car for no reason. What set it up like that?
Okay, I sense an entrance cue. Is this where cosmic inflation comes in? How does it tackle these head scratchers?
Exactly. Inflation is the leading idea. It proposes this period of hyper-fast, accelerating expansion incredibly early on, like around 10 to the minus 34 seconds after the theoretical start. This burst is thought to be driven by huge energy density locked in the vacuum of space itself. The energy scales are just mind-boggling. 1026 Kelvin,
Hmm.
way beyond our particle accelerators, which hints that inflation might be tied to unifying forces, maybe even quantum gravity.
So superpowered expansion phase right at the beginning.
Right. And quantum uncertainty is key here. At those energies, space-time itself gets fuzzy, quantum effects dominate. Maybe the universe's origin was a quantum event. Inflation can potentially solve both problems. It takes a tiny, smooth patch of space, smooth because it was small enough to even out, and blows it up exponentially fast. That creates the vast, smooth universe we see. And the structure, those tiny quantum fluctuations, the wobbles, inflation stretches them too, right up to cosmic scales. They become the seeds for galaxies. And importantly, as Kinney notes, this isn't just hand-waving. Inflation makes specific predictions we can actually test with observations.
Okay, that's wild. So a tiny smooth bit gets inflated, and tiny quantum jitters get stretched into the first clumps for gravity to work on.
Yep.
Got it. How does this fit with the cosmological principle and the universe's expansion that Hubble saw?
Well, the cosmological principle, the idea that there's no special place, the universe looks the same everywhere on large scales, fits perfectly. Inflation naturally produces that large-scale uniformity. And the expansion observed by Lemaitre and Hubble, where galaxies recede faster the farther away they are, inflation sets the stage for that expansion, kicking off the hot Big Bang phase after inflation ends. That relationship, V equals H0D, uses the Hubble constant. Kinney mentions we have a good handle on its value, but there's still some, tension in the measurements, a bit of a controversy.
The Hubble tension.
Yeah. And it's crucial to ditch some old misconceptions. The Big Bang wasn't an explosion in space from one point. It was an expansion of space itself everywhere at once, like Kinney's grid analogy. Imagine points on a grid, and the whole grid stretches. Everything moves away from everything else. And that initial singularity, it wasn't a point in space. It was a moment in time, the beginning of time, as far as the model goes.
Okay, space itself stretching, not an explosion point. That helps. But if space is stretching and light takes time to travel, that limits what we can see, doesn't it? Tell us about light cones and the observable universe.
Absolutely. In relativity, we talk about space-time. Objects trace paths called world lines. Light travels at the ultimate speed limit. So from any event, a point in space and time, there's a boundary defined by light speed. That's the light cone. The future light cone is everything that event can possibly influence. The past light cone is everything that could possibly have influenced that event. Anything outside is, well, causally disconnected.
Can't affect it, can't be affected by it.
Right. And because light takes time, looking out is looking back. Deeper space means earlier time. The Big Bang singularity puts a fundamental boundary on our past light cone. We can only see light that's had time to reach us since the universe became transparent. That defines our observable universe. It's a finite sphere centered on us. The edge is the cosmic horizon. We literally can't see beyond it yet.
So we're inside this bubble of visibility, constantly expanding as light from further away reaches us. What's in the bubble, though? We keep hearing it's mostly not the stuff we're made of. Dark matter, dark energy.
That's spot on. The atoms we know baryonic matter are only about 5% of the universe's total energy budget. Seriously, just 5%. Most of it is dark. Doesn't interact with light much, if at all. First, there's dark matter, about 26%. It clumps gravitationally, just like normal matter. It forms these huge invisible halos that galaxies live inside. It's like the scaffolding for cosmic structure.
We don't know what it is.
Frustratingly, no. We haven't directly detected the particles yet, despite lots of experiments. It's a huge mystery. Then there's dark energy. That's the biggest slice, about 69%.
Hmm.
It's weird. It seems smooth, it's spread out everywhere. And unlike matter, its density doesn't drop as space expands. Its gravitational effect is repulsive. It pushes space apart, causing the expansion to accelerate. We figured that out by looking at distant supernovae.
And the best guess is vacuum energy.
That's a leading candidate, the energy inherent in empty space itself. But the theoretical value and the observed value are wildly different, so another big mystery.
Okay, 5% us, 26% mysterious clumpy stuff, 69% mysterious smooth stuff, pushing everything apart. How did these proportions change over time?
They change because they dilute differently as space expands. Kinney explains this well. Matter density, both dark and normal, just goes down with volume. Space doubles, density halves, simple enough. Radiation, like the photons of the CMB, dilutes faster. Why? Because the volume increases and the photons lose energy as their wavelengths get stretched by the expansion that's redshift.
Okay, radiation fades faster than matter.
But dark energy, if it's vacuum energy, its density stays constant. So as space expands, the total amount of dark energy actually goes up. More space, same density everywhere means more total energy.
Wow, okay, so its influence grows over time.
Exactly, which leads to different eras. Very early on, radiation dominated because it was so incredibly hot and dense. Then, as things cooled and expanded, matter took over. We call that the matter-dominated era. That's when structure really started to grow. But eventually, maybe 8 billion years ago, the ever-present dark energy finally became dominant over the thinning matter and radiation, and that's when the expansion started accelerating. We're in the dark energy-dominated era now. Kinney's figure 2.6 shows this transition nicely.
That makes sense. Radiation fades fastest, then matter, then dark energy takes over. Can we zoom back in again to those super early moments? What were the key milestones right after the theoretical start?
It's a blur of activity. Around 1034 seconds, maybe? The strong force might have split from the electroweak force. Huge energies, 1026 Kelvin. This is also the likely energy scale for inflation. Maybe the matter-antimatter imbalance got locked in around then, still very speculative. Then a bit of an unknown period. Maybe dark matter formed between 1034 and 1012 seconds. Around 1012 seconds, the electroweak phase transition. The Higgs field turns on, particles get mass.
Okay.
Then 10 to 6 seconds, quarks and gluons cool enough to form protons and neutrons. We've actually made this quark-gluon plasma in labs like RHIC, briefly. Then comes Big Bang nucleosynthesis, maybe 1 second to 3 minutes. Light nuclei form helium, lithium, neutrinos decouple, electrons and positrons annihilate, leaving loads of photons, the future CMB. Around 60,000 years, matter density finally overtakes radiation density. Dark matter starts collapsing gravitationally. 300,000 years, recombination, electrons join protons, neutral atoms form, the universe becomes transparent, CMB photons are free, start of the cosmic dark ages.
No stars yet.
No stars yet. They finally ignite maybe 1 billion years later, ending the dark ages. And now, 13.8 billion years on, here we are, universe at 2.7 Kelvin. If you trace it all back, mathematically, you hit that singularity, infinite density temperature. But our physics breaks down way before that. Before 1043 seconds, the Planck time. That's quantum gravity territory. We just don't have the theory yet.
It's just staggering, those time scales, those temperatures. So we look out, we see back in time, but only to that CMB wall, that surface of last scattering. What does that ancient light tell us, and what puzzles does it throw up?
Well, first, it tells us the early universe was simple. Mostly hydrogen, some helium. Heavier stuff came later, from stars. Before recombination, above 3000 Kelvin, it was a plasma. Opaque. Photons bounced off electrons constantly, like light and fog. As space expanded, those photons got redshifted. Their wavelengths stretch. It's not Doppler shift from motion through space, it's the stretching of space. They act like little clocks, telling us how much expansion has happened. So, the CMB, detected by Penzias and Wilson, some of that old TV static was CMB, is that light finally released at recombination. Now, if you subtract our motion, we're moving towards Leo at 370 kilometers, creating a dipole pattern. the remaining CMB is incredibly isotropic. The temperature is the same everywhere to 1 part in 100,000.
Which sounds smooth, but you said that's a problem.
It's the horizon problem. Look at opposite sides of the sky in the CMB. They are separated by way more distance than light could have traveled between the Big Bang and when the CMB was released. They were never in causal contact. They couldn't have communicated to agree on the same temperature. So how did they end up exactly the same temperature to such high precision?
They couldn't have shared heat or information.
Exactly. The standard model offers no explanation. Just saying it started that way feels like saying it was magic. It's deeply unsatisfying.
Okay, the universe is too smooth for its own good, according to the standard model. How does inflation fix this particular problem?
Inflation's solution is elegant. Remember that exponential expansion. It takes a tiny region, small enough to have been causally connected and reached thermal equilibrium before inflation started, and stretches it so vastly that it becomes larger than our entire observable universe today. So points that were once close enough to share heat are now flung to opposite sides of our sky. They look causally disconnected now, but they weren't initially. Inflation connects their pasts. Kinney's figure 4.2 shows this visually.
Ah, okay. So the smoothness was established before inflation blew everything up to enormous scales. That makes sense. What about the flatness problem? How does inflation handle that one?
Same principle, basically. We can measure the universe's curvature using patterns in the CMB. These acoustic oscillations act like standard rulers, and the measurement says space is incredibly flat. For it to be this flat today, the standard model requires the initial curvature right after the Big Bang to have been tuned to 0 with unbelievable precision. Another fine-tuning problem. Inflation solves it by stretching. Think of a balloon surface. If you zoom in on a tiny patch of a huge balloon, it looks flat, right?
Yeah, locally flat.
Inflation does that to the universe. Whatever initial curvature might have existed, inflation stretches space so much that our observable patch looks almost perfectly flat today. Figure 4.3 illustrates this idea.
So inflation is like a cosmic steamroller, flattening curvature and smoothing out temperatures. Amazing. But wait, if it made everything so smooth, where'd the galaxies and clusters come from? We need some lumpiness.
Right. And inflation explains that too. It doesn't just explain the uniformity. It explains the origin of the tiny deviations from uniformity, the seeds of structure. The idea comes from quantum mechanics. During inflation, the vacuum wasn't perfectly empty. There were constant quantum fluctuations, tiny temporary variations in energy. Inflation took these microscopic quantum fluctuations in the field driving inflation and stretched them to astrophysical scales.
Whoa, quantum jitters become cosmic seeds.
That's the idea. These stretched quantum fluctuations became tiny variations in density across the universe at the end of inflation. Slightly denser regions, slightly less dense regions. Gravity then goes to work on these initial seeds over billions of years, pulling matter into the denser regions, forming stars, galaxies, clusters, the whole cosmic web.
That is profoundly cool. Quantum physics setting the blueprint for the cosmos. Okay, you mentioned the inflaton field and vacuum energy driving this. Can you unpack that physics of nothing a bit more?
Sure. Quantum field theory says even empty space, the vacuum, has energy. These quantum fluctuations give it a non-zero energy density. And crucially, this vacuum energy can have negative pressure. In general relativity, negative pressure acts like anti-gravity. It drives accelerated expansion, perfect for inflation.
Yeah.
Now, where does the specific high vacuum energy for inflation come from? One idea is symmetry breaking, borrowed from particle physics. Imagine a pencil balanced on its tip, unstable but symmetric. It falls, picks a direction, breaks the symmetry, and settles into a lower energy state. In the very early universe, forces might have been unified, symmetric. As it cooled, symmetries broke, forces separated. This breaking process can release energy, changing the vacuum energy state. Think of a potential energy landscape, like a Mexican hat. The field starts at the high, unstable central point, symmetric state, and rolls down into the brim, lower energy, broken symmetry state. The inflaton field could be like this. Rolling down its potential energy hill releases energy, driving inflation. It's similar to the Higgs mechanism, where the Higgs field breaks symmetry and gives particles mass. The inflaton provides the temporary high vacuum energy needed for that inflationary burst.
So a transition from an unstable nothing to a more stable nothing powers the whole expansion. That's mind-bending. Are there different ways this could happen? You mentioned different inflation models.
Yeah, the details are still debated. Gough's original old inflation had issues. Then came new inflation. Lind, Albrecht, Steinhardt, with the field rolling slowly away from that unstable symmetric point. Linda also proposed chaotic inflation, where the field might just start high up on its potential slope and roll down towards a minimum without needing symmetry breaking right at the start.
And this slow roll keeps popping up. Why is rolling slowly so important?
Slow roll is key. For inflation to last long enough to solve the horizon and flatness problems, the inflaton field needs to roll down its potential hill very, very slowly. Two things help. The potential needs to be very flat, like a gentle slope, not a steep cliff. And the expansion itself creates a kind of friction, an expansion drag that slows the field down. While it's rolling slowly, its energy density stays nearly constant, acting like that temporary cosmological constant, driving exponential expansion.
Got it. Gentle slope, cosmic friction.
During this phase, the universe is expanding like crazy, but it's actually very cold and empty, because any initial particles get diluted away. The horizon is tiny, maybe grapefruit-sized. Inflation ends when the field reaches the bottom of the hill and starts oscillating. These oscillations decay into regular particles, dumping the inflaton's energy back into the universe. That's reheating.
So that's how we get the hot Big Bang soup back.
Exactly. Reheating connects the cold, empty, inflationary phase to the hot, dense, early universe of the Standard Model. The details are messy and not fully understood, though.
Oh, and inflation also solves another problem, magnetic monopoles. Some theories predict lots of these heavy magnetic particles, but we don't see them. Inflation dilutes them away to near invisibility.
Okay, so inflation smooths, flattens, creates the seeds of structure via quantum fluctuations, solves the monopole problem, and then reheats the universe. That's a lot. How exactly do those quantum fluctuations become density variations? It connects back to quantum uncertainty and dynamic spacetime. Remember, Wheeler, space tells matter how to move. Matter tells space how to curve. Even empty space buzzes with quantum activity zero-point energy. Think of the Casimir effect, or even Hawking radiation near black holes. These hint at the reality of vacuum fluctuations. During inflation, these quantum fluctuations aren't just happening in space, they are fluctuations of the inflaton field itself, the thing driving the expansion. As space stretches exponentially, these tiny quantum fluctuations get stretched too, right along with space. Microscopic quantum effects become macroscopic density variation.
Felt by the expansion.
Precisely. Inflation also predicts that quantum fluctuations in space-time itself, gravitational waves, should also be stretched, creating a background of primordial gravitational waves. Detecting those would be huge confirmation.
So the structure we see originated as quantum noise. How big were those initial density differences?
The amplitude, Kinney explains, depends on the ratio between the size of the quantum fluctuations and how fast the field was classically rolling down its potential. It also depends on the expansion rate during inflation. These fluctuations are random, following a Gaussian or bell curve distribution, mostly small variations, fewer large ones. We describe their strength across different scales with the primordial power spectrum. Inflation predicts this spectrum should be nearly scale invariant, meaning fluctuations had roughly the same strength on all size scales, but with a slight tilt. Observations from the CMB match this prediction incredibly well.
Wow. Okay. It really feels like inflation weaves together quantum physics and cosmology in a remarkable way, solving major puzzles of the standard Big Bang. As we wrap up, what are the absolute core takeaways from Kinney's exploration of inflation?
I think the main thing is that inflation provides this powerful, testable framework. It gives compelling answers to why the universe is so big, so smooth, horizon problem, and so flat, flatness problem. And maybe most profoundly, it offers a causal mechanism for the origin of cosmic structure. All the galaxies and clusters tracing them back to quantum fluctuations in the very early universe. It connects the quantum world to the cosmos.
Yeah, that connection is just astonishing. This deep dive really highlights that intersection, doesn't it? The physics of the huge and the physics of the tiny coming together to explain the beginning.
Absolutely. It's an incredible synthesis. But, it's important to remember it's not the final word. The absolute earliest moment, the physics right at the singularity or what came before inflation, if anything, that's still frontier territory. That's where we need quantum gravity, a deeper understanding of space-time itself.
So a powerful theory, but the quest continues. That leaves us with something to really chew on, doesn't it? Even with inflation, the ultimate beginning remains shrouded. Maybe something for you, our listener, to ponder. What does it mean for the universe to have a quantum origin? And what secrets might a theory of quantum gravity unlock? The universe definitely keeps posing fascinating questions.